Hello and welcome to a few more examples from Chapter 1, CSE 259. In this, we will look at mathematical induction. So mathematical induction has two main steps. One is the base case, which is the minimal case, and the induction step in which we take a hypothesis for any general value k and then prove it for the next value k plus 1. So let's jump into a few examples straight away. So here is one. Use the principle of mathematical induction to verify that for n, any positive integer 6 power n minus 1 is divisible by 5. So n is greater than 0. So looking at the base step, that is P1, where n is equal to 1, we have 6 power 1 minus 1 is 5, which is clearly divisible by 5. So P1 holds, that is the base case, holds. Now we move to the induction step, and our hypothesis is that Pk holds, that is 6 power k minus 1, where k is any positive integer, is divisible by 5. And then we go about proving this for Pk plus 1, which is 6 power k plus 1 minus 1 is divisible by 5. For this, we split 6 power k plus 1 as 6 into 6 power k plus 1. And then we subtract 6 and add 6. So these are simple tricks that would come with practice, which will help us in solving mathematical induction steps better. So here, what we do is from the first two, take out 6, and we get 6 power k plus k minus 1 plus 6 minus 1. And now you get the final equation, which is 6 into 6 power k minus 1 plus 5. Now this here is something you can notice is similar to what we did in the hypothesis step. So that is 6 into 6 power k minus 1. In this term, 6 power k minus 1 is divisible by 5. That's what we took as the hypothesis. So 6 times a number that is divisible by 5 is clearly divisible by 5. And the second term is 5, which is divisible by 5. And hence, 6 power k plus 1 minus 1 is divisible by 5. That is Pk plus 1 holds. So we have proved that 6 power n minus 1 is divisible by 5 through principles of mathematical induction. Let's look at another example. N factorial is greater than 3 power n for n greater than or equal to 7. Now here you notice that n, the base case, is n greater than or equal to 7. So what happens in the base case? So P7, where n is 7, is n factorial, which turns out to be the value 5040, and 3 power 7 is 2187, and so we see that this holds. Now when we look at the induction step, for k greater than equal to 7, we suppose that Pk holds, that is k factorial is greater than 3 power k. And now we need to show that Pk plus 1 holds, that is k plus 1 factorial is greater than 3 power k plus 1. So we can write k plus 1 factorial as k plus 1 times k factorial. And from the hypothesis step here, we can replace k factorial by 3 power k, and we get this equation, that is k plus 1 factorial is greater than k plus 1 times 3 power k. We also know that k is greater than or equal to 7 from the equation. So we can say, replacing k by 7, we can say this is greater than or equal to 7 plus 1 whole power 3 power k. Now this value 8 is greater than 3. So we get it's greater than 3 times 3 power k, that is 3 power k plus 1. So Pk plus 1 holds. And so by principles of mathematical induction, we have proved that 3 factorial is greater than 3 power n for n greater than or equal to 7. Well, what happens if n is less than 7? You can check it out that this does not hold. Try out the math and have a look. Another example over here. So 2 times 1 minus 1, 2 times 2 minus 1, and so on, adding those terms till n is equal to n squared. or the thing is, n square can be represented as a sum of integers multiplied by 2 subtracted by 1. So again, using the principles of mathematical induction, the base case is for n equal to 1. So here n equal to 1 will be 2 times 1 minus 1, which is 1, and so this is true. For the induction step, we assume pk is true, that is 2 times 1 minus 1, so on till 2 times k minus 1 is equal to k square. So this is our hypothesis. And then we try to show that pk plus 1 holds, that is 2 times 1 minus 1, so on and so forth, till 2 times k plus 1 minus 1 is equal to k plus 1 whole square. So now let's consider the left-hand side. That's this. And here, from the hypothesis step, we can replace this entire value by k square, that is this term. So that is from pk step. So that leads to k square plus 2 times k plus 1 minus 1. And expanding this equation, we get this quadratic equation. And when we solve this quadratic equation, we get k plus 1 times k plus 1, which is same as k plus 1 whole square. So from this, we see that the equation holds. So we have proved pk plus 1 holds. So by principles of mathematical induction, 2 times 1 minus 1 and so on and so forth till 2 times n minus 1 is equal to n squared. So this is it for the examples. To know more, look at the book and also look at some of the notes provided to you on your canvas. Thank you.